Okay, cool. Okay, so we talked about one-dimensional optimization on Monday, and it wasn't arguably it wasn't the most exciting thing we've ever seen. It was a lot of optimizing things that look more or less like parabolas. But the reason it's useful to talk about is because one-dimensional optimization gives us some intuition behind when you might use first or second order optimizers. And you'll remember that in one dimension, you can usually get pretty far using gradient descent. But sometimes it's better to use second order methods like Newton's method, which use second order information about how convex or concave your potential is to converge faster. And so in exchange for faster convergence, so fewer steps of gradient descent, you had to do a lot more computations. And this is a general dichotomy in optimization. So the problem I'm going to be using, just because it's easy to draw and pretty, is multivariate Gaussian optimization. So I'm just going to define some landscape that we're trying to minimize that exists in 2 dimensions. So my landscape is just a series of upside down Gaussians. I have P of them in a d-dimensional space. And for this case, I can actually compute my gradient analytically. Is there a question over there? Okay, cool. So we can compute the gradient analytically. And so if the loss function takes a 2 vector and returns a scalar, the gradient is a 2 vector as well. And so my implementation is vectorized, so there's nothing too exciting there. But the landscape we're looking at looks like this, where it has spurious local minima, but it also has a true global minimum somewhere in the domain. Okay. So in this particular case, because I defined my loss landscape analytically, it happens to be the case that I can find an analytic loss, so I can compute this gradient. I'm going to use this more or less directly. In the case where that isn't true, which is usually going to be the case for most problems that we care about, the question is how can it get around not actually knowing the gradient analytically? And we saw one way of doing this in the last class, which is that you can just do finite differences. So here I'm going to implement a basic grad check function. And you'll see these pop up a little bit in machine learning. But the idea is that I have, in this case, an analytic gradient for my function. And I can compare the analytic gradient against a finite difference approximation. Okay, so I have my analytic grad, which should give me some number. And then I just here pick some epsilon neighborhood and find the centered finite difference approximation around that neighborhood. Okay, and in terms of that, if I use a small enough epsilon, the true gradient, which is me actually symbolically finding the gradient of my potential, is pretty close to the numerical gradient. So this is pretty reasonable. Oh, because that gives us some intuition behind how I might be able to do optimization if I don't know the gradient analytically. However, there is a cost associated with this, which in this case is equal to these 2 calls to the loss function. So the time cost of computing finite difference gradients is order d, where d is the number of dimensions that your gradient lives in. Okay, so in this case, I have a 2-dimensional potential, so the time cost is order dimension 2. But if I had something like a really high dimensional problem, then this linear cost of finite differences would grow really quickly. And when we talk about deep learning, we'll talk about how you get around that time cost of computing very large gradients or very high dimensional gradients. Okay. So I mentioned this last class, but I just think it bears reiterating, right? So here I'm able to draw a picture, and I can see that my minimum is here. Drawing a picture implicitly involves calling the loss function at every single pixel on this plot. That works in 2 dimensions, but if it even takes 10 microseconds per call or per call to the loss function, if I have something like a 7-dimensional Gaussian landscape, I can't do that on my computer anymore. And if I had something like a typical machine learning model, which lives in dimensions of, let's say, order 1 million, the runtime of doing this globally would, be of order the age of the universe or something. So while it's possible, to draw this picture in 2D, in a 1-million-dimensional optimization, good luck. And this is why we're going to have to use all of these all these local methods like gradient descent. Okay. So I have this landscape, and I want to find the location of this minimum using as few calls to the loss function as possible, because those are really expensive. And this is always what I'm trying to do, is just minimize the number of calls to the loss function. Okay, so the obvious first thing I could try to do that uses purely local information would be gradient descent. We saw this in 1 dimension, but it's a lot more interesting in multiple dimensions. So multivariate gradient descent is exactly what it always is, which is if I have some potential function, so it's a scalar function that takes a vector argument, the gradient of that function can be interpreted as always pointing in the direction of maximum ascent. So when I find the gradient, I get for free the steepest direction, which is kind of nice about multiple dimensions. So if I want to walk down to find the minimum, I just take a step negative in that direction. And just like we saw before, I get one hyperparameter here, which is I'm going to call it the learning rate. And this is how big a step I take before I do another measurement. Okay, so intuitively, that eta parameter, if it's really, really big, right, I measure my local slope and I say, okay, that looks good. And I take a huge jump. But I run the risk of maybe overshooting my minimum or something like we saw before where we got oscillations. Conversely, if I pick this to be comically small, I won't have to worry about that, but then I'll be putting in a ton of calls to my loss function, right? And we saw before that like we don't want to put in endless calls to the loss function because that's going to be very expensive when you have million dimensional optimization or something. Okay, so the way I'm going to implement this, and I'll use this throughout the notebook, is rather than implement every optimizer piecemeal, I'm just going to define a base class that's going to do all the boring stuff. And then I'm just going to change out the logic of how it does the optimization. Okay, so my base optimizer class is based off of the PyTorch base optimizer class, if you've used PyTorch before. It's going to take the loss as a keyword argument, so a little bit different than we did it before. And then it's going to take all my hyperparameters, bind them to the class as instance attributes. And then it's going to have a generic fit method that just runs however many iterations of my heretofore undefined update rule until either I run out of iterations, so it optimizes for 1,000 by default, or if it notices that the gradient is no longer changing, it's just stuck at one point, it'll stop early. So this will take at most max iteration calls, but it could take a lot less just to save me a little bit of compute if needed. Okay, so this is exactly like how we implemented gradient descent and other optimizers before. I'm just wrapping them all in this base optimizer where all of the storing intermediate steps and initializing the random seed, all of that stuff is written into the base class here. And the only thing that's going to get changed out is going to be this thing called update that actually is going to implement the logic of gradient descent. Okay, so that's my base optimizer class. We're going to see this once and hopefully never have to look at it again. So that's what it looks like. And then you'll notice I use a template form where I have an update that just raises an error because I haven't defined that method yet. Okay, so if I want to implement normal gradient descent, that's just going to inherit from the base optimizer, and I just have to define a single method there. So that's super nice that I can define the specific case of gradient descent as an optimization algorithm as inheriting from this generic base case. Okay, so this is the update rule for gradient descent. Here's what it looks like in terms of code. Here I have an analytic estimate for the loss. So I'm just going to use that, but I could replace with the finite difference if I had a case where that wouldn't work. Okay, and then my learning rate is my eta here. So this is all I have to do, and this update method is a child process or a child method that will get called in the parent's fit method. Okay, so that's what that looks like symbolically. So let's see if that works. So I'm going to run that cell to get both into memory. I'm going to instantiate the child class, but you'll notice the child class doesn't have any keyword arguments. It doesn't even have a constructor. And so all of this stuff is going to pass right on through to the base class constructor. So I've given all of these different arguments. If I didn't specify some of them, they would just revert to their defaults. But you'll notice I do give it the loss function in the constructor of the class. Okay, so that's my optimizer. So far, it hasn't done anything. It just is storing all of the hyperparameters that define the optimization. I need to pick an initial point for my optimization. So I'm just going to pick some random point throughout this domain. And in fact, it looks like I picked 100 random points. That way, make it a little bit more interesting. So we're going to start this optimizer at 100 random points. Each of those points, we're going to run this loop that's going to do this gradient descent update rule. And the reason I don't have any extra code for the fact I did 100 points is because all of this is vectorized. So it implicitly is going to use that extra dimension. Yeah, what's up?
Don't you have to call the init function?
So because of so this is using a trick. In this case, I didn't have to do super init. And that's because it's going to implicitly pass everything to the parent. That's just because of how I structured that. So there are cases where you don't have to do the super init. Yeah. But if I did have the super init, it would work. It just would be unnecessary for this. It's just a way to save a little bit of code. Yeah, that's a good question. Okay, so let me go ahead and run this. So I think that this ran really quickly. Yeah, okay. So I just ran for 100 different starting points that are just randomly chosen to lie within this domain. It ran vanilla gradient descent. Okay, so that looks something like, let's see if this works. Okay, looks like it did. So these are my initial conditions, randomly sampled 100 points, and this is where they ended up. You can see a lot of them went to local minima, some of them went to this global minima, and some of them didn't go anywhere. So what happened there? So the first thing that I can do is I can just look and see what the loss as a function of time for each trajectory is. You'll sometimes see these called learning curves in the context of machine learning. So each grade trace here is the loss of a single one of these 100 points. And then the black curve is the average across the 100 to see what's happening in general. Okay, so as you might expect, because we're doing gradient descent, the loss monotonically decreases. That's good because there's no mechanism to go uphill here, so that should happen. But you can kind of suss out what's happening here, which is that some points don't go anywhere. Their loss doesn't decrease for all of the iterations I performed. Some points seem to find minima, which correspond to these shallow points. So they just plateau because they just found their nearest local minimum. But some of the points did manage to find that really deep minimum. So you can see that there's these sort of striations that correspond to my different local minima here. And it looks like there's 4 points here and there's 4 local minima. So that makes sense that we see that. But on average, I see continuous decrease because when different points find their nearest local minima changes. So the average looks like a continuous decrease. This curves like this that show loss decreasing over time are really popular when in machine learning, where people are training really large iterative models where you want to see your loss continuously drop during training, usually. Okay, so that gives us some intuition, and these curves are very common, which is why I show it. But I think a better way of showing this is that because this is a two-dimensional landscape, we can quite literally visualize the trajectories. So the trajectories of this optimization look like this. Where you can see kind of what goes on here, which is that basically every point makes a beeline for the nearest local minimum. And that makes sense because gradient descent has no ability to do anything at all except just fall downhill. So these points roll to their nearest local minimum. But you'll notice that out here, there are a few points that don't do anything, and that's because this is where effectively the potential is flat, so there's no gradient to roll on. Okay, and that's the still picture, but I think that the videos are still working. So here's what this looks like if you do it as a slider. And one of the things that's kind of cool here is that you can see that the points that start out really far away, there is still a gradient, but the gradient is super weak. So you get these little straggler points. They're stuck in flat regions. And so they sit for a really long time, and then eventually they find a potential and they actually fall. And these correspond to these really late drops that you see here, where you have these points that basically didn't do anything but then abruptly fell. And one of the interesting things about high dimensional optimization is that there's results that show that a lot of your points often will be near these really flat regions. So if you run your optimizer really long in order to get them out of these sort of really flat regions where there's not a lot of gradient information. Okay, so gradient descent is super bound to the geometry of the landscape, and the flat regions will always descend a lot later. Okay, so that's vanilla gradient descent, and it's just the multivariate generalization of normal gradient descent. And gradient descent's, it's arguably the one optimization algorithm to know because a lot of methods used to optimize large models are more or less variants of gradient descent. And it's nice because you implicitly need one call to the loss function or one call to the loss gradient function per time step to compute it. Okay. So I won't get into this today, but I'll just point out that a lot of the dynamics that we saw here are very strongly dependent on what we chose for our learning rate. We talked about this a little bit last time. And here it looks like I chose a learning rate that was small enough that I didn't get any weird behaviors. Okay, and this might break, so maybe I'll regret doing this, but I'm gonna try running this with a larger learning rate to see what happens. We'll see. I might just pick a big one to see if this works. Okay, yeah, it looks like something bad happened. Great. Okay, so let's see what that video looks like because I think that that's usually nicer to see. Okay, so here all I've done is I've just cranked up the learning rates, the size of the steps, and we'll see what happens here. I haven't actually run this. Okay, so so it looks like my learning rate was still big enough because it looks like a lot more points were able to find the minimum there. So basically, all that increasing the learning rate did here was it amplified the size of the steps, and so more of the points converged. Um, okay, and now just I'm going to try running a super big learning rate to see if we can get this to go unstable. So let's do like 4.3. Oh yeah, okay, great. So if I use a super big learning rate, now I'm going to start to see problems. Yeah. Okay. So what happened here is if I just changed the learning rate to something big, it's a little hard to see, so maybe we'll do the first few steps. In one step, the points basically make a giant beeline down the gradient. And while that's good for the points that are really far away, the points that are once they're in the side of the potential, they're basically oscillating. And that's because like I started over here, I compute a giant gradient, that shoots me over here. Now I still have a gradient and I shoot back. And so I'll end up with points that just oscillate for a really long time. Um, yeah, and those points in there, you'll notice that they sort of collapse to this interesting manifold there. And this is the danger of setting your learning rate too high, is you'll get these oscillations. It's a little forgiving, but you can see that this is like a common failure mode that we saw even in univariate optimization. Okay, so learning rate's a parameter of the optimizer, so it's a hyperparameter, and it's important to set it correctly because if I set it too tiny, the points out here get stuck forever. But if I set it really big, whatever this is happens. Okay, so there's one modification I could make that might be pretty sensible, which is that we talked about last class how this update rule here, where I just take a step along the gradient by some learning rate, this more or less represents overdamped dynamics. So the obvious thing to do would be to try using underdamped dynamics. So I do this little derivation here. It's not super interesting, but just to get a sense of where this comes from. If I think about each point in my optimization landscape as being acted on by a force, so X is going to be the position in that landscape. Here we're working in 2 dimensions. I can always write the kinematics of that right as a force balance here. So this is your gradient along the potential, and then maybe you have some damping. Okay, so when we use gradient descent, we're implicitly making this assumption that this damping ratio is really, really big, and so the double derivative term disappears from the equation. And what that means is that you can then sort of rearrange terms and just say that x dot is equal to the gradient of the potential locally, where the potential is the loss function we're optimizing. So gradient descent is formally equivalent, at least at small learning rates, to just overdamped dynamics. And that's why you never see really exciting stuff happens, because you just fall down a hill, you can't overshoot or anything because there's not really any source of inertia. So what we can do instead is we can try adding inertia back in by keeping the second order term in the dynamic, so keeping the double time derivative. So if you sort of plug and chug with the math, I show this derivation, but it's not that exciting. The updated rule for what the dynamics would look like in discrete time if we kept the second order time derivative would be the exact same gradient descent update plus a term that depends on the most recent value of your position. Okay, so this is a change in where I was now versus the previous time step. So you can think of this as like a velocity over a single time step. So now we have an extra term here. This almost acts like a memory or a momentum that keeps me going in the direction I was going before. So all I'm going to do is I'm going to take my optimizer from before, and I'm just going to modify it to have this additional term in it that gives me the second order underdamped dynamics. Okay, so in order to implement that, I do need to use my super method now, and the reason is because now I'm going to pick up a new hyperparameter. So I have 2 hyperparameters now. I have the learning rate, same as before, but now I want to have a tunable amount of momentum. This is like the mass of the particle as it falls. So I need to pass that to the keyword argument of my child class. And so I need to use super to say which arguments go to the parent and which go to my child. So here I use super and I say to all keyword arguments I give it go to the parent and the loss goes to the parent. But then momentum, which wasn't defined in the parent class, that's a keyword argument that's going to be tied or bound just to the child. So the base optimizer doesn't have a momentum keyword argument, but the child does. Okay, other than that, as long as I'm willing to do that and define this gradient term, then all I have to do again is just change the update rule. So before for gradient descent, it just looked like this, but now we have this additional term that looks like the momentum, which is just this difference, times this parameter, which sets how much mass the particle has. So we now have two hyperparameters for this optimization. Okay, so that's gradient descent with momentum, and it's basically a one-line change that includes this history-like term. Okay, so let me make sure I have that loaded. Great, and I'm once again going to take 100 initial conditions scattered throughout the domain, and I'm just going to run this optimizer for a bunch of steps and see where they end up. Okay. So that, again, my initial guess is all over the place, and it looks like my final guess is starting to get pretty good. I still have a couple of points that didn't make it anywhere, but now you can see a higher fraction trajectories look like they found the minima. At least they found a local minima, and maybe more found the global minimum. Okay, so if I draw my loss curve again, I can start to see a little bit more of what's happening. So the one thing that becomes very clear right off the bat is that a lot of points fall and find the global minima super quickly. My guess is going to be that those are going to be points that were already within this sort of cluster of basins. But then there's other stuff that pop out that's kind of nice. The other thing that pops out is that the average across all of these trajectories is a lot sort of smoother. So rather than sort of falling in steps, it looks like there's always trajectories that are sort of going at different times. And we'll see what that looks like in the picture, but that's just one thing that's notable about momentum is that you get smoother loss curves. And in general, it looks like this got a little bit deeper on average than it did when we just had normal gradient descent. So momentum looks like it improved our optimization some. Okay, so let's look at what the videos look like. So that's what the still trajectories look like. So you can see there's probably something crazy going on there. So let's look at the video. Okay, so these are my initial conditions. And I'm going to start the optimization. They're going to start going. And you can see now what happens when you have momentum, which is we can actually get pretty complicated dynamics inside the basin. So rather than just falling to the minimum, you get points like this one that comes in from really far away, and it basically orbits a while, sort of rattles around the bottom of the potential. And this is the classical example of the difference between overdamped and underdamped dynamics, right? If I have an overdamped system like a spring on a block, if it's overdamped, it just goes straight to its fixed point. But if it's underdamped, it'll actually oscillate for a while before it finds whatever the equilibrium point is. And that corresponds to when the energy has sort of left the system. So here, these trajectories that come in from really far away, they're falling in one direction for a really, really long amount of time. Like I like this one as an example. So let's go back. So this blue guy here, it's moving along a straight line for a really long amount of time. And so when it finally hits that basin, it really majorly overshoots it. And you can see it orbits for a really long time in there. Yeah, so momentum adds the second order term, and it looks like it maybe helps points sort of find a little bit more complex dynamics. And you can see a little bit about why momentum is useful, which is you can see here that I had a case where it looks like a particle fell into this basin, overshot it, then fell into the deeper basin. And that would be impossible in vanilla gradient descent because there's no physical mechanism to go uphill if I have normal gradient descent. But with momentum, if I come in with enough momentum, I can shoot and fall over a basin. So it looks like this might give me some help here. Okay, so momentum is used quite a bit. A lot of modern optimizers like Atom is used a lot in machine learning. A lot of those optimizers don't just do gradient descent, they have a momentum-like term. And there's fancier variations that maybe have less clear analogies to physics, but which have this idea of using the memory of your past steps to sort of inform your optimization steps. Okay, so that's gradient descent and gradient descent with momentum. And so then the other thing you could imagine doing that has sort of a dynamical analog would be adding noise to the optimization steps. So this is going to be gradient descent with stochasticity. Okay, so stochastic gradient descent has the interpretation of a particle undergoing motion subject to a potential in the presence of something like a Langevin noise term, so Brownian motion forcing you. I'm going to not include momentum here because I think it's too complicated. So we're going to just go back to standard overdamped dynamics of a particle falling to the bottom of a potential. But then I want to add something that acts like white noise, forcing that particle all along the way. And in thermodynamics, you think of this as like, random jostling due to a thermal bath. We're not going to be quite so interpretive. We're just going to say that this is some noise term in my dynamics. And for our purposes, we're going to focus on additive noise. So basically, I do gradient descent, then I just add a random number. So the implementation is pretty simple, but it has this interpretation of sort of Landry-Vaughan dynamics or something because we have no correlations. Okay, so I write a little bit about it here, but in practice, if I assume that whatever my stochasticity source is, that it has no time correlation, so it's a delta function correlated noise, that means that any time lag destroys their correlation structure, then that means that every time step of my optimization, I can treat this like a random vector. So I don't have to worry about keeping track of the past values of the noise. I just can sample a new random vector. And this is again due to this assumption that I have Landry-Vaughan noise. Okay. So in the case of Brownian noise on gradient descent, I can use sort of a simpler formulation. So once again, to define this optimizer, I do have to introduce a new hyperparameter, which is the noise amplitude. So as a result, I have to use a super method again, which is going to tell my constructor to use these as parent class arguments, and then to define this new keyword argument. So whenever I introduced a new hyperparameter, I picked up a new class attribute associated with the child. But having said that, the actual update rule is super simple, which is that I'm going to compute the gradient. I'm going to do my gradient descent update, which is just this. But then rather than just do that, I'm also going to add my random noise to my gradient. So I'm going to compute this random vector. This is a two-dimensional optimization, so this will be a random two vector. And it turns out that delta correlated Brownian noise is equivalent to drawing a random normal vector. So each element of this vector is drawn from a Gaussian distribution. Okay. So let's see what this looks like when I add that noise in. And I'm going to set, some suitably small value of the noise. Okay. So that's where I started out. And this is where my particles ended up. And you can start to see what's happening, which is that I actually cleared out a lot of my domain. So a lot of points found their way in. But once they found their way to the bottom, because this noise force is always active, they don't just quietly sit there. They still jostle around a little bit. And that's because the way I did my noise is just linear. So I just always have that present, even if this goes to 0 here. Okay. So now, my loss term looks kind of different. You start to see that I have the jostling of that Brownian motion present in my loss curves. And then my trajectories look a lot crazier. So that's what they look like if I draw them all at once. They're kind of all over the place. But the video is where you start to see what's happening. So even the guys that are out here still move around, right? Because that noise is always present. So that could be useful because now, even if I have no gradient information, there's at least something causing these to move. So these guys sort of jostle around. And some of them jostle around until they find an area with a high gradient. This is a really good example here where that point wasn't really doing anything. It was just taking a random walk. But then eventually it starts to find an area with gradient information. And then it just makes a beeline for the nearest minimum. And then I think in this video, we'll see if I have any cases of this. Okay. There is one case in this video, I think if I ran it for longer, where you could see actually cases where a random noise pushed out of one basin to another. So you have at least one mechanism of crossing barriers between basins if you have this white noise active. Okay, so this gives me a little bit of something because at least means that I can do some random walking when I have no local information. And this is important because remember that usually when I'm doing optimization using gradient descent, I don't know a priori where my minima are, right? I can't just search my entire space because it's very expensive. And so these points here basically have 0 information to go on. And so at the very least, rather than just having them sit the entire optimization, I can at least nuzzle them in random or nudge them in random directions to hope that they find something. The reason that this doesn't globally converge is because my landscape really far out here is still flat. So some of these points take a random walk and find the edges of these basins and they fall. But you can see in the video that some of these points basically just wander off. I think this point's a good example. And they basically just don't ever come back, right? And you can guess that in high dimensions, random walks generally don't recur. And so as I go to higher and higher dimensions, my optimization, a higher fraction of points will sort of wander off and not find my minima if it looks like this. So stochastic gradient descent gets me something, but if I have a landscape that doesn't have a lot of forcing or doesn't have a lot of minima, I still have this issue that random walks are very inefficient in a few dimensions for finding things. But nonetheless, it gets me something. Okay, so that's stochastic gradient descent. It's just, yeah, what's up?
Computational costs.
So I guess here I do pick up a cost of order D, which is just I have to sample D random elements for that random vector. So in this case, this is two-dimensional optimization, so it's not as bad, but a million dimensions, I have to sample a million dimensional vector and add it. However, I don't have to do any extra calls to my loss function, which can often be a lot more expensive. So it doesn't pick up any asymptotic speedups, but it at least is a way to do something that doesn't involve calling my loss function again. Yeah. Okay. So I think that vanilla gradient descent, momentum, and stochastic gradient descent, those three ideas are most of what you need to know to understand modern large-scale optimization. These giant deep learning models that people train for image classification or nowadays for generative models, these use slightly fancier optimizers, but they all have things that look like stochasticity or look like momentum. They just have slightly different interpretations. So a lot of how training goes with really large models, you can understand in terms of the idea of, if I have very little gradient information, I can get stuck. If I have too much gradient information, I can overshoot and oscillate and stuff like that. A lot of those phenomena pop up even in modern state-of-the-art training of large models. Okay, and then there's one fine point. I think I wrote about it. Yeah, I write about it up here. So one thing to watch out for is that when you encounter stochastic gradient descent in the context of training a model, oftentimes you aren't actually adding the noise. The noise comes from the fact that I randomly subsample my data. And there's theoretical reasons for that, but I'll just point out that here, because I'm actually have a physical landscape I'm searching, I have to come up with a random vector. But if I'm approximating a landscape using data sampled from some experiment, I can fake my noise by subsampling the data and getting random batches. So that's just a slight difference in how stochastic gradient descent shows up in machine learning. But I wouldn't worry about that too much for now, unless you're doing machine learning. Okay, so all of this is just our basic optimizers in multiple dimensions. So the other thing that comes up a lot in optimization is cases where you have constraints acting on your system. And this is the subject. There's entire graduate course at this university about how to deal with constrained optimization. It's a whole branch of computer science. We're going to do the simplest possible version of it just to give a flavor of what this looks like. And this is just projected gradient descent. So the idea here is, in this case, let's suppose that I'm trying to optimize in this two-dimensional landscape, but I have a hard, strict one-dimensional constraint that has the form of an equality. So in this case, I'm going to write my equality as the sum of the squares of the elements has to equal 1, which is equivalent to saying that my trajectories have to be constrained to lie on the unit circle. That's all that this condition implies. I here is the index into the dimension of the vector. Okay, so now, maybe I want to minimize some loss function, but I have to minimize it subject to the fact that at the end of optimization, the sum of the squares of every point need to equal 1. So it needs to lie in the unit circle. So there's a lot of different methods for doing constrained optimization when you have equality constraints. But the simplest one that I like to use here is just projected gradient descent. The idea here is actually super simple, which is that I'm just going to run gradient descent. And then after every single step of gradient descent, I'm just going to project onto the constraint. So I'm going to take a step towards the minimum of the unconstrained function, and then I'm going to take that step and project it onto the unit circle. And this sounds really insane, but this is actually the basis of a whole family of first order optimization methods. And we'll see that it actually works surprisingly well for this really simple problem we're doing here. Okay, so projected gradient descent is going to have a little bit more to it than our previous optimizers, because we're going to have two methods in our optimizer now. Okay, so I'm going to define it as a child of our base class. I actually think I don't need this. I'll leave it just because I'm scared, but I'm pretty sure that it's not necessary because I don't have any new keyword arguments. I have to define an update method, and the update method is first going to project onto the constraint. So I'm going to need a projection method. Then it's just going to compute the gradient and do gradient descent after the projection. Okay, so that requires me to define one new method associated with my class, and this is just going to implement this constraint and this projection onto that constraint. So in this case, I'm going to just hard code this unit circle constraint. So I'm just going to take my vector, and it turns out that projecting onto the unit circle is equivalent to just converting it to a unit vector. So projection is super simple when I have an equality constraint. of this form because it's the L2 norm. Okay, so my projection thing will just take any vector and find the nearest unit vector along its direction, and I claim that that is projecting the system onto the unit circle, so this satisfies this constraint. Okay, so my projected gradient descent optimizer is just going to keep projecting onto that unit circle, computing the gradient, and then if any components of the gradient that point off the unit circle, it's going to zero out. Okay, so this is my implementation, so let's go ahead and load that. Let's get that into memory. And now this. And once again, I'm just going to run it for my 100 different initial conditions. Okay, so those are my initial guesses. And that's where they ended up. So it looks like the points basically make a beeline for the unit circle. Again, that's because of the projection. And then once they find the unit circle, it looks like they all ended up on it. So we'll look at what the video of this looks like to maybe get a little bit more intuition. Okay. So the first step of projected gradient descent wasn't that exciting, which is I forced everyone to go to the unit circle. That's just my projection operator. But the next steps are actually kind of cool. So we're on the unit circle, and all we're going to do is we're going to compute the gradient globally for the unconstrained problem, and then just project it onto the unit circle. And you can see what happens. I'm going to try to do this nice and slowly. So this kind of is nice because it does what you'd expect, which is that on some level this becomes a one-dimensional optimization problem. It's just that that one-dimensional manifold is a circle embedded in the space of the full optimization problem. And so what happens is that when I'm like out here or something, if I compute the gradient vector here, it probably points this way. But then because I have this projection step, that gradient vector is going to get dot producted with the constraint. And so I'm only going to retain the part of it that points along the circle. And so that ends up sort of pulling me towards the local minima. So I still find the local minima, but they're the local minima of where the circle intersects with the potential, which is kind of cool. Okay, so this is kind of a coarse method of doing constrained optimization, but you could imagine cases where maybe instead of doing this really hard projection, I do something a little bit softer, like maybe I tell it to take a step towards the circle instead of forcing it onto it. And there's a whole family of methods. I mean, there's this whole book, Boyd and something, that talks about how you can take this basic idea and make it a little bit more elaborate. But equality constraints almost always involve some form of projection onto the constraint. Okay, so that's gradient descent, momentum, stochastic gradient descent, and then how you do constraints. We won't talk about inequality constraints for now because that's its own subfield. So this is cases where maybe I want the norm of the constraints to satisfy an inequality instead of lying exactly on the unit circle. And there's whole theorems about that. And there's this giant textbook that I think the textbook is 800 pages. And then there's a slide deck I link on the syllabus that's 200 pages. So I don't know how concise it is, but you're welcome to take a look at that if you do constrained optimization. Okay. I think I will probably skip Lagrangian duality. Yeah, okay. So I won't talk about this now. I'll just mention that you can get pretty elaborate with other ways of enforcing constraints. So I think a lot of folks have probably seen Lagrange multipliers before, not just in classical mechanics, but it also pops up sometimes in multivariate calculus. The Lagrange multipliers are another way of satisfying a constraint. And I'll just mention that oftentimes when you have a Lagrange multiplier in your problem and you're trying to do it numerically, it makes sense to increase the strength of the Lagrange constraint over time. And there's good reasons for that. It's called Lagrangian duality, and there's a whole set of notes here that talks about it. But Lagrange multipliers, I think I'll skip because I don't think anything really exciting happens here. And we'll talk about regularizers later with machine learning. Okay, so everything I just talked about was what I'd call a first order method. I call it a first order method in the sense that I have my loss function. My loss function has this API where I give it a d-dimensional vector. It gives me a scalar. And so all of these methods like gradient descent just involve basically the first derivative of that scalar function because I just have to use the gradient, which is a d vector. Okay, so just like we saw in one-dimensional optimization, there's a whole family of methods that use second order information about the loss landscapes, the concavities. And in multiple dimensions, that means that instead of just computing the gradient, which is a vector, we have to compute the Hessian, which is a matrix. So the Hessian matrix is the matrix of partial derivatives of some potential with respect to each of the coordinates. And this is the generalization of the concavity, because this matrix basically tells me how much my potential varies along each coordinate dimension. So you can think of the eigenvectors of this matrix as telling me sort of which direction my potential points along, which directions are stiffer, which are softer, and this or that. So this encodes something about the geometry of that landscape in terms of its stiffnesses or its concavity in different directions. Okay, so remember that the whole reason we cared about the second order information in the case of one-dimensional optimization is that it allowed us to basically replace the learning rate with a deterministic term. Oh, he took away my chalk. How? But budget cuts, I guess. The chalk over here. Wow, did he really take over the chalk? Okay, I guess I could draw this. That's what I get for complaining about the chalk. I guess. Oh, thank you. How? Okay, so in one dimension, we saw that like we did x of n plus 1 is equal to xn minus eta f prime. And then in order to do second order methods, I just said, forget it, I'm just going to do 1 over f prime prime. And so then Newton's method basically ended up replacing this term with 1 over f prime prime. So we basically scale the learning rate by the local concavity. We can basically do the same thing in multiple dimensions, but now, you know, I can't just take 1 over a matrix. I have to use a matrix inverse, so it's a little bit more painful. But Newton's method is quite literally the same idea, which is that I compute my loss vector, so that's a d by 1 row vector. And instead of doing 1 over the concavity, which is not really a number, I have to actually find the inverse of this d by d matrix. But this is equivalent to doing 1 over f prime prime. It's just nastier. Okay, so Newton's method in multiple dimensions is a second order optimization method. And this is where things start to get kind of cool, because I find this d by 1 vector, I find this matrix of partial derivatives, which is d by d. Matrix vector multiplication gives me a d vector, and that's what I update by. And you can think of this as adapting your learning rate separately for each dimension of this column vector. So it's like I have a different rate at which I'm going to take a step along every single coordinate direction. Is ideally what this H matrix should do. Okay, so you know, I have this random Gaussian landscape, and for now, we're going to assume that I can calculate this Hessian analytically. But you could imagine you could maybe use finite differences to find this, or maybe there's more elaborate methods out there. But for now, I'm just going to calculate analytically. So it turns out that analytically, you can find that the Hessian of a random Gaussian landscape looks like that. Who knew? So I'm going to update my function, my random loss landscape, to now have a Hessian method. And you'll notice I use Einstein notation. So if you're interested in linear algebra with NumPy, you can do this here. Okay, so I'm just going to optimize this landscape now that I have explicit Hessian information to call. Yeah. Okay, here I'm just plotting this. I'm plotting the eigenvectors of the Hessian there, and looks like there's some interesting curvature structure there, but that's whatever. Okay, so my multivariate Newton method, I'm going to just write this as a new method just because this has a lot of extra steps. So I have all my standard stuff. You'll notice that I don't have a learning rate in the constructor because I don't need one, because the learning rate is set by the Hessian. And so then my fit is just compute the gradient, just like I do in gradient descent, compute this d by d matrix, find the inverse of it, right, because it's inverse Hessian, do this really nasty matrix multiplication, and then I just update by it. And I think I added momentum just for fun, but that's not really necessary here. So at every step of this optimization, for all of these steps in this loop, I'm going to have to do this d by d matrix times d by 1 vector multiplication. So this should take d cubed operations per loop. So the runtime here, I'd say, is d cubed times the number of iterations. Okay, so that's a lot of work. So hopefully this is going to get me something good. Let me get that in memory. You'll notice that was a little bit slower. So gradient descent ran almost instantaneously, but you'll notice that chugged for about 2 seconds. So that's already a hint that matrix vector multiplication is a little expensive. Okay, so if I run that here, things get a little bit crazy. So the points that converge super fast. The points for which there's very little gradient information didn't go quite so well. You can see that I had a little bit of problems out here. Let's see what that looks like in the loss landscape. So the points that found the local minimum found it really fast, but some points got stuck really early. So if I had no gradient information, I actually did a lot worse with second order optimization. And let's see what my video looks like for this. So this is the first time step. And basically, I showed it on the lines there. The points that converge really quickly, but I get points that get stuck at unstable points. And then I have some points that actually go off to infinity. They sort of wander off forever. And this is the danger of second order methods, which is that if you have a landscape that has saddle points or has flat regions, you can really get stuck for a long time on them. So second order methods won't get you everything. But when they work, and these work really well for very convex landscapes that have very deep local minima, they usually will be a lot faster. So that time cost I pay to do that giant matrix multiplication, I get back if I have a very convex landscape. Is the intuition behind when I use the second order method. Okay, so the last thing I'll mention, and I talk a little bit about why this didn't go well for this problem. So the last thing I'll mention, right, is that the whole idea behind doing this is this intuition. The whole idea behind doing this matrix inverse is this intuition that I need to adapt the learning rate to how steep it is. It's just that this does it separately for every dimension. So there's a whole family of methods that are called quasi-Newton or quasi-second order methods that basically try to get the benefits in terms of speed of gradient descent, but combine that with a sort of simplicity, or combine that with the sort of adaptivity of second order methods. And the idea here is kind of simple. I do this whole derivation here. But you can imagine if I had some really complicated landscape that had a lot of different directions, that had different stiffnesses, maybe rather than taking my learning rate and adapting it separately for every dimension, I just care about whichever dimension is the most steep or the least steep. So second order methods try to bypass computing the full Hessian by instead adapting the learning rate based off of the largest eigenvalue of the Hessian. Which I argue we know that for a diagonal matrix, the eigenspectrum is just 1 over the eigenvalue, or is the inverse of a diagonal matrix, just 1 over the diagonal elements. So this to leading order should approximate the inverse of the matrix if it's dominated by one direction. And so quasi-Newton methods, the simplest method would be to just compute the eigenspectrum using the power method, find the largest eigenvalue, and just divide your learning rate by that scalar. And this is your simplest possible adaptive learning rate that captures the essence of what full Newton would do. And I'd argue that this is a lot faster because we can use the power method rather than finding a full d-cubed matrix inverse. And I show a little bit of code as to how that works, but the TLDR on that is that it is pretty good. It's a little bit better than Newton's method. All right, so that's multivariate optimization, and we'll see it again when we talk about deep learning, which is a lot of optimization problems. So, all right, thank you.